India's green hydrogen ambition is one of the boldest energy bet in the world. 5 million metric tons annually by 2030 under the National Green Hydrogen Mission. But every kilogram of green hydrogen begins with one device, the electrolyzer. Its efficiency determines your power cost. Its capital cost determines your project's bankability, and whether it is made in India or imported will determine who captures the value of this transition. Today's guest has spent nearly 3 decades at the frontier of electrochemical engineering. He reduced precious metal usage in PEM fuel cells by 40 times at Los Alamos National Laboratory, led 7 product generations at Bloom Energy, and now as Chief Science and Technology Officer at Ohmium International is helping build one of the world's largest PEM Electrolyzer Gigafactories right here in Bengaluru. He holds 49 issued patents. The world of green hydrogen knows him simply as Dr. Chockkalingam Karuppaiah. Dr. Chock. I am your host, Dr. R. Venugopal, former Joint Chief Controller of Explosives at PESO, where I was a part of licensing India's first hydrogen dispensing stations. It's a genuine privilege to welcome Dr. Chock to the flaming microphone. Welcome, Dr. Chock.
Thank you, Dr. Venugopal. It's a pleasure to be part of this Flaming Microphone podcast.
For our audience of engineers, startup founders and regulators, what does your role at Ohmium actually involve day to day?
Yeah, as Chief Science and Technology Officer, I'm responsible for the current product technology. So essentially, the electrolyzer as a system, the stack performance, and how it runs in the field. That's today's product. And at the same time, I'm also looking at the product roadmap. What comes next year, beyond 2 years, 5 years down the road. So from the roadmap of product, I'm also responsible for that. On a day-to-day basis, I'm looking at the time between the R&D and engineering team and looking at what's happening in the manufacturing and what's happening in the field and talking to customers to understand what the real needs are. So the gap between spec sheet and what happens in the real world is where most of the things are. And I spend a lot of time in that to understand and ensure that we are meeting the customer expectations.
So looking after the customer's need.
Exactly. So a technology is only as good as it fulfills the customer's needs. That's why I make sure that it's connecting to what we develop internally.
You worked in Los Alamos, Plug Power, Case Western, Bloom Energy, and now at Ohmium. Very different organizations. What is the single problem you have been trying to solve across all of them? It's
when I hear this question, it takes me down the memory lane, right? So after graduating from CECRI with BTech, started research in PEM fuel cells. And from that time onwards, I started looking at the efficient way to generate energy, use energy, generate chemicals, and use chemicals. So that's the overall electrochemical device. That's the common thread. If you go zoom in a bit, in the technical point of view, there is this device with a membrane in between, right? So it can be polymeric membrane, it can be a separator in the case of battery, or it can be a ceramic membrane in the case of solid oxide fuel cell. So when you zoom in, that's the common thread. Specific further to say what is it that connects and what differentiates my career path is using the fundamentals to solve the applied problems. Let me give an example because that's a generic statement, right? I was a senior scientist at Plug Power, 2 years, fresh out of PhD. I was sitting in a meeting with the systems engineering team.
Okay.
And they were talking about this inverter. So essentially, the fuel cells generate the DC power.
Absolutely.
And then you invert it to convert it to AC and then connect it to the grid. Right. This inverter, while you're connecting it to the fuel cell stack, it introduces an AC ripple on top of the DC load. And now this clicked and said, okay, if it's going through AC ripple, do I have enough fuel in my fuel cell stack so that I'm not starving the anode?
Okay.
So connecting that systems problem to the fundamental problem that I need to solve in the stack. For example, what is my dynamics within the stack so that I have enough fuel during the up cycle of that AC ripple?
Absolutely.
And during the up cycle, if I didn't have the dynamics like fuel there, is the material stable to meet that?
Absolutely.
So I approached it through an engineering problem, looking at the volume in the stack, as well as the materials problem to make it robust down the line. So that's one example of how I take the fundamentals and then ensure that it solves the systems problem.
Absolutely.
So that's the common thing.
Common thing within all this.
All these, right? When you look at that, helps with, for example, if you go the different dimensions, it can be minimum material utilization. You mentioned about the 40x reduction in the actual noble metal use in the fuel cells. So to make it commercial, the cost has to be low. For the performance, it has to be efficiency. For the operational cost, it has to be the life. I always tell my team, to be a world-class team in this electrochemical device, in the electrochemical industry, it's performance and cost and life. It's not an or, it's and. So that's the common thread across all of these.
In plain terms, what does an electrolyzer do? And why is it so central to decarbonizing refineries, fertilizers, hard-to-abate sector like steel and heavy transport in India?
Yeah. Let me start with a simple explanation of electrolyzer. And a lot of us in high school days probably did some water electrolysis in the beaker, taking either a couple of copper electrodes or graphite rods. Even in my high school days, I used to take the battery out and get the central carbon electrode, use that, and then electrolyze water, generating hydrogen and oxygen. Right? Of course, that's the fundamental, but when a real system, you're actually supplying electricity and water, splitting water to generate hydrogen and oxygen. That's the core principle. Now, as long as that electricity is coming from renewable sources, like solar, like wind, then it's green hydrogen. So that's the core of what the electrolysis is. Now, coming to the decarbonization aspect, so when you look at the key industrial sectors, refineries, ammonia synthesis, steel manufacturing, all of these are using hydrogen today. Where does that hydrogen come from? It comes from natural gas or coal. You convert natural gas through steam methane reformation to hydrogen and CO2, or you have the steam pass through coal and then generate hydrogen and CO2. That emits CO2. Right, there's a 10-to-1 factor, 10x of CO2, 10 kg of CO2 to 1 kg of hydrogen. Sometimes it's 12, depending on the source. So 10 to 12. This hydrogen is utilized today. When you replace that with green hydrogen, you avoid all these emissions. So that's why it's one of the critical sectors to be decarbonized. And I call this as must-have hydrogen, not an optional hydrogen. What do I mean by that? So when you say, let's say you have transportation, okay? Today's transportation up to 400 miles or 600, 700 kilometers, batteries can fit in the need, right? There, hydrogen, let's say because of supply of lithium and other things, you can switch to hydrogen as the source. That's an optional hydrogen because we can always get batteries and replace that. Whereas in the industrial case, it's a must-have. It's not like you can put a battery and then create this ammonia, create steel or anything, right? So you need this source. And for that must have hydrogen. The key enabler of decarbonization is through electrolysis technology.
So that's a simple definition on electrolysis. Alkaline, PEM, solid oxide. Where does PEM clearly win today? And where do the other technologies still hold the edge?
Sure. One of my industrial in-plant training when I was at CECRI was to Maytur. It's a Chemplast company called Chemplast, and it's a chloralkali company.
Yes.
So you take sodium chloride and electrolyze it to produce caustic soda and chlorine, right?
Yeah.
So that's the origin for alkaline technology.
Okay.
Essentially, chloralkali used initially a diaphragm-based separator as a separator in the electrolysis cell. That's exactly the same technology in the alkaline today. With that, because these diaphragms are porous in nature, the key factor from safety point of view that needs to be maintained is the pressure balancing, the hydrogen and oxygen. And we all are aware of the volumetric ratio difference between hydrogen and oxygen. With H2O, it's twice the volume of hydrogen versus oxygen that you're producing. And that leads to a very precise control of this gas phase, right? So when you're dealing with alkaline, what is the pedigree? It's decades-long performance in terms of because of the pedigree of the chloralkali. So there's that experience base that's there. What needs to be maintained is this gas pressure. So where it can work is a base load, where it's always running, you're not going up and down. So there's a base load capacity of producing hydrogen where the electricity is consistently being given. Alkaline is good, right? So you can go there. Now, let's go to the solid oxide, and then I'll come to the PEM. Solid oxide, I spent nearly more than a decade, 12 years total at Bloom Energy, working on solid oxide fuel cell, which is the reverse of solid oxide electrolysis.
Yes.
Right. So in the solid oxide cell, you're taking the world's most fragile material, a ceramic membrane. And for high temperature stability, you're taking chrome-based metal. It's literally 95% chrome and remaining iron. That's the alloy that's used because that's what's stable at close to 1,000 degrees Celsius. Now, you take the most fragile material and the most hardest material, seal them together, take it to 1,000 degrees Celsius. Now, the coefficient of thermal expansion that needs to be matched between these two is in parts per billion level. Today, there's not even equipment to measure that CTE. So what we used to do is do a differential measurement by using the components. Now, as a result of this tight CTE match to be done and operating temperature, it doesn't like going up and down, right? It's, again, always on power is how the fuel cells are. Same thing with the solid oxide electrolysis. The other complication, or I would say system complexity, that adds to the solid oxide electrolysis, which is where its benefit also derives from, is you need to supply water as steam.
Okay.
So you need to supply thermal energy, right? So when you look at the thermodynamics of water splitting, it's the same, independent of the technology. It's how much of electricity you provide, how much of thermal energy you provide. In solid oxide electrolysis, if you have waste stream energy that's available, thermal energy that's available, that can be used to convert water into steam. In that case, and it's always running, then solid oxide electrolysis can work. Okay.
Sure.
Now, coming to the PEM. Okay. So we know the renewables go up and down. Right, it's a dynamic, and the cloud comes, your solar power, and the wind stops blowing, you stop the wind power, right? So you should be able to go up and down, the dynamics.
Yes.
And then the other benefit of PEM technology is the footprint. So let's take a stamp, right? A stamp size, roughly 1 square centimeter, 1 centimeter by 1 centimeter. Now, one of the metrics in electrochemical device engineering is called current density. How much current can you pass through this stamp size? So in alkaline and solid oxide electrolysis, it's in the range of 0.4 to 0.7. That's the amount of current you can pass in that 1 square centimeter. In the PEM, on the other hand, it's 1.4 to 2, some are even higher than that. Right? So it's multiple times over in terms of the current density. And that helps reduce the footprint that's needed.
Okay. So if you rank the main drivers of green hydrogen cost, power price, efficiency, capex,
Correct.
financing, regulation, which one can technologically actually move in this decade?
Yeah. Let's maybe look at the components of levelized cost of hydrogen. Okay. Now, when you look at the majority of that cost, or I would say one of the major fractions, as you alluded to in the beginning, is the kilowatt hour electricity used. So that comes from both the, let's call it the external factors beyond the Ohmium, the four walls of Ohmium and other electrolyzer companies, and then what's internal. So electricity cost, I would say, is about 50% of the total cost of hydrogen.
Okay. 50%
will be the electricity cost.
Okay.
Right. The next layer is the 30% is the capital expense. Capex. And then the 20% is the OPEX. OPEX without the electricity cost.
Okay.
Right. So that's the rough math.
Okay.
Right. Now, how can, let's look at the roadmap of these. Right. So when you look at that electricity, as renewable sources, solar, wind, all of these keep coming down, the cost keeps coming down on the cents per kilowatt hour that is external to the electrolyzer suppliers. Now, internal to the electrolyzer suppliers, how can you attack the electricity cost? It's through efficiency. So when you look at what our third generation stack technology, the stack efficiency is at 45 kilowatt hour per kilogram and the system efficiency is at 48 kilowatt hour per kilogram. So when you use less kilowatt hours, so overall expenses go down. So the internal to that, the technology can really help to ensure that your electricity cost is addressed through that. The second layer is the capex. Okay. So we have a healthy roadmap of bringing the cost down. This is where all the material reduction, and there is this common thread of and condition, right? It's performance and cost and life. So now the third pillar, which is the operational cost, is the life. So the technology can address all of these. Now, in a project, so now I've zoomed in on the system. When you take a zoom out on the project level, there is the cost of capital that's coming into play. The cost of capital, there is certainly prevailing interest rate, but there's also the risk premium that the financiers add because the projects are not this is a first of a kind project or a second of a kind project, and they put in a risk premium.
Yes.
So that's a financial cost that gets added. And those are some of the things where the policies can come into play.
The risk premium for the new hydrogen projects is much more than the already existing projects.
Yeah, that's correct, because they're looking for bankability, looking at the data that's coming out there. This is why increasing the number of projects will help increase the confidence, and as a result, the risk premium can be minimized.
You came from the field of fuel cells. What genuinely surprised you when you moved to designing large PEM Electrolyzers?
It's an excellent question because when I'll tell you the challenges that I was solving when I was at a fuel cell. So in a fuel cell, PEM fuel cell especially, you're ensuring that this membrane has conductivity maintained through humidification. You need to maintain that membrane is wet through a vapor phase transport. Okay. Now, at the same time, you don't want water condensing on the cathode side because oxygen is trying to get in. You want to make sure that performance is good. So that's what we called as the water management in a PEM fuel cell. Coming into the electrolyzer, I said, hey, this is liquid water already. I don't have to worry about two-phase and other things, and it should be simpler, right? So now the key thing is with respect to, because water is moving in the fuel cell in a vapor phase state, lot of salts that will impact the performance, either membrane or the catalyst, their vapor pressures are very low. So they don't get carried as a vapor through the water vapor. Whereas in the case of electrolyzer, liquid will transport those salts very easily.
Yes.
So water purity is part of the water management. The second one, when you go into the technical aspect, because the audience is lots of technical technically sound audience, I want to cover that. As protons are moving through the membrane, for every proton, there is 3 to 5 water molecules that move. In an electrolyzer, you also have liquid water on the anode side. There's a concentration gradient that moves into the cathode side. So that leaves liquid water along with hydrogen. There's a phase separation, water management. So these are some surprises. Of course, we had solved it because the systems are running in the field now. But those are surprises as I moved from fuel cell to electrolyzer. Yeah, exactly.
Your 40-fold precious metal reduction at Los Alamos is legendary.
Yeah.
How confident are you that Iridium will not become the bottleneck for global PFM scale up?
Yeah, personally, I'm very confident on this, and the reason is not coming from some a gut feeling or anything, intuition. It's based on the actual data and what we had been able to do. So we had made it publicly announced that we are at 18 gigawatts of electrolyzer per ton of iridium, and our internal roadmap is working towards doubling that further with 36 gigawatt per ton. So that's further microstructural engineering in the catalyst layer to help reduce the amount of iridium needed. Along with that, there are alternate architectures that we can work on to get to near zero iridium or at some point completely eliminated. So as the technologies evolve and the roadmaps evolve, I think I'm very confident on this, and that's based on the data that we have seen internally.
Ohmium chose India as its global manufacturing base quite early.
Yeah.
What made that a clear decision? Is it a talent supply chain or policy or proximity to demand?
I would say all of the above, and let me actually go into the specifics. I mentioned I graduated from CECRI.
Yes.
CECRI, Central Electrochemical Research Institute, I think most of the audience will be aware, but it's a CSIR institute that got founded in 1957. They had been doing all aspects of electrochemistry: corrosion, batteries, fuel cells, electroplating, electrochemical sensors, all aspects of electrochemistry, pyroelectrochemistry, high temperature electrochemistry, aluminum synthesis, all of that. Right. 1988, Professor K.A. Vasu had this vision that he needed, I don't know how he got, he foresaw what's coming down the pike. And he created this Bachelor's in Technology course in 1988.
Oh.
I was part of the second batch of students who joined. Right. So every year, it's still true till today, in the entire world, CECRI is the only place where you can get undergraduate in electrochemical engineering.
Yes.
And that's 40 students or 45 students per year. And they're all distributed through India and in the world as well. And the talent of course, you need more than electrochemical engineers to build the systems. You need mechanical engineers, electrical engineers, controls engineers, manufacturing engineers. So all of that through NIT, IITs, local engineering colleges, all of them are contributing. The talent is certainly number one. Number two, supply chain. One thing, as you're manufacturing, one is the labor cost, for sure. That's a contributor. But beyond labor cost, it's also the supply chain, extended enterprise. How can we approach that? That's key aspects of the India First strategy. Number three, when you look at our involvement and with NTPC, we have won PLI schemes with SECI for the electrolyzer. All of these interactions working with the government institutions cannot happen sitting in California. So all three led to an India First strategy: skills, supply chain and cost, and regulatory policy, and making a difference. And I will touch on a personal note. People talk about brain drain and all the other things. And here I am sitting after graduated from CECRI, and being able to come back and contribute to India's hydrogen story and growth is personally satisfying as well.
That's a great news.
Yeah.
Dr. Chock, Ohmium's Mark III achieves 48 kWh per kilogram at beginning of life.
Yeah.
What does that number mean in practice for our project cost and for emissions avoided versus grey hydrogen?
Yeah. So let's take, for example, the cost of electricity today in India. And let's say it's 3 rupees per unit, right? Let's call that the best renewable cost. So when you take a look at the kilogram of hydrogen produced, you need 48 times 3. For ease of simplicity, let's call it 50. It's 150 rupees just for the electricity. Now, when you look at the capex and opex, so you can start adding those components. There are credible industry analysis that shows that with the progress in the renewable cost coming down, with the electrolyzer cost roadmap coming down, you can get to 300 rupees per kg.
300 rupees per
kg today.
Today, okay.
Right. So now, but that's not as good as the grey hydrogen, which is at 150 to 200.
Absolutely.
Okay. Now, how do we bridge that gap?
Yes.
So one is certainly the further reduction in the renewable energy cost. Let's say 1 to 2 cents per kilowatt hour. That comes down. And our internal cost roadmap also reduces the capex of the electrolyzer for it to come down. With this, you will be able to get to roughly 150 to 200, even 250 by 2030. There is credible industrial analysis to show that.
Great.
So with that, we will get to the parity.
Okay.
Now, I briefly touched on the emissions earlier.
Yes.
It's the factor of 12 kg per kg of hydrogen emissions avoided.
Yes.
Now, when you look at our capacity, annual capacity, it's 2 gigawatt from our Bengaluru facility, can be scaled up later. That's multiple millions of tons of CO2 avoided.
Yeah, absolutely.
So this is a real dent. So what we need is projects so that we can start implementing them.
Correct. We will pause here. In the episode 2, Dr. Chock will walk us through Ohmium's full system architecture, share field lessons on safety and standards, honestly at what India hydrogen decade means for Indian industrial future.